在我身后就是 VLT 甚大望远镜的等比骨架。8.2米的主镜呢，使它成为了目前天文研究上的主力选手。我们不光在地面上有望远镜，在太空上呢，我们还有服役了30年的哈勃空间望远镜，以及即将进行它科研任务的詹姆斯韦伯空间望远镜。这是一片20米乘50米的停车场，而韦伯空间望远镜的太阳风帆呢，将会占据这个停车场一半的面积，而6.5米的主镜呢，将会帮助我们看到宇宙最初始的样子。为此呢，我邀请到了即将使用 JWST 进行观测的朋友，来和大家聊下属于韦伯时代的天文学。So today I invite my friend Jorryt Matthee to join my video channel and talk about JWST. Jorryt is a Zwicky fellow and working at ETH right now. And his research mainly concentrated on the galaxy formation and universe reionization. And he will have 18 hours observational time on JWST as a principal investigator and more than 100 hours as a co-PI on JWST. So welcome, Jorryt.
Thanks. Yeah, sounds good. If it launches.
Yes. So what can we expect on JWST? Is there any difference compared to the previous telescope we had?
Yeah, there's a big difference. I mean, yeah. We were all very excited about JWST. I mean, we were waiting for a long time now. I mean, when I remember as a kid that it was supposed to launch in 2012 or so. I mean, the main thing, it's going to be the biggest telescope in space, yeah, which is on itself is already exciting. The mirror is 6 meters compared to 2.5 meters from Hubble. It just means you have much more collecting power, collecting area. But the most exciting thing is the coverage, is the wavelength coverage. So compared to Hubble, James Webb can finally give us spectroscopy in the infrared at wavelengths beyond 2 micron. And that is going to be, in my opinion, the major breakthrough.
How far we can look by this JWST telescope? Because when we talk about the telescope, people always think about how far we can look, what's the magnification for the telescope, and yes, how far we can look using this telescope.
Yes, that's a good question. Yeah, well, the real answer is we don't really know how far it can look, at least. All right, to explain this a bit, so, you know, like the light has a finite traveling speed. So if we look at any object, we always look in the past. Even if I look at you on my screen, I look 10 to the minus something seconds in the past, right? If we look at if you look at the sky, and particularly if we take very deep images, like very long exposure times that we can see objects that are extremely faint, then we will look very far away. So what happens is that the universe expanded, is still expanding, which means that objects that are further away, the light of their stars redshifted. So the intrinsic light is basically redder than it was emitted. And that means that in order to see the optical light of a very distant galaxy, you need to look at the infrared. So what are the expectations for JWST? So the most distant galaxy currently known is at a redshift of about 11. So the universe was 12 times smaller than it is today. And that's a few 100 million years after the Big Bang. Currently we are 13.7 billion years after the Big Bang. So it's about if I do that correctly, it's about like 5% of cosmic time. That we're looking. The question is, so James Webb should be able to look further than that. So we should be able to find galaxies at even higher redshifts. but it's just uncertain how many there are. It depends on how galaxies grow, whether they grow very quickly or not, or gradually. If we look at what people are finding with the Hubble Space Telescope at redshift 9, which is the highest redshift where you can get like statistical samples with Hubble, there's actually a lot of uncertainty. So whether there will be a lot of redshift 15 galaxies or none, but JWST is actually not, it's very hard to predict. Simulations give us an idea, but well, those simulations are not, they're very good, but they're not simulating every single detail that's relevant. It's just too complicated to do. So yeah, we don't know. In principle, I think if I would bet, I would expect detection of galaxies redshift 17 or so, 15, 17, I think something like that. I mean, the question is, so it may be able to detect those galaxies, but then the challenge is also to actually confirm that the thing you see, the little blob you see, is such a distant galaxy. And that may be actually more challenging. It will be more challenging, but it remains to be seen whether that's doable or not.
So if we think the galaxy is like a human, so redshift 17 galaxies is like a child baby, right?
Yes. Yeah, it's a bit similar. We can think like that. I actually like to think about it in terms of archaeology. We're basically doing excavations, and it's not exactly a good analogy, but basically, we are like digging in, like the deeper you dig, the more distant you look in the past on Earth as well, right?
Yes.
And we are, you can find I don't know, skeletons of babies. You can also find skeletons of adults. In the very early universe, there's basically no time to grow adults, right?
Yeah.
There's no time for galaxies to grow up. So we are not expecting to find adult galaxies in the very early universe. If we would, that would actually be changing everything, right? Because it would mean our understanding of the age of the universe is wrong.
So you will have 18 hours observational time on the JWST. So can you talk to us, how do you get this observational time? I mean, how do you apply for that? How the procedure goes?
Yeah, of course. This is applicable to JWST, but actually to almost all telescopes like Hubble, like Keck on Hawaii, Subaru, and VLT in Chile. So there's always what happens is there is some amount of time available for JWST, the people who built the instruments and who were involved already 20 years ago in the developing the telescope. They have been awarded time, so they don't have to apply. Just as that's what you get basically if you build it. But there's a fraction of time which actually is like half. I think it's half or slightly half. It's a considerable fraction of time that is open to anyone in principle, and it's called general observing.
Yes.
And there was a call in November last year for proposals, and you had to write. Basically, everyone could write a proposal for a project to do with JWST. After everyone submits it, it goes to a panel that reads the proposals. What's relatively new is that it was anonymous, so in principle they did not know who we were. They were not told who the applicants were.
Okay.
To be fair, the field is not that large. Right?
Yes.
Not that many people doing this on the world. So if you are reviewing such things, you have a rough guess. But at least whether a student or a big professor is leading the work, you actually don't know.
I had an interview before, and some professor asked me, so if I have a JWST, what's the first object I will look at? So I tell him I will look at some clusters because there are a lot of galaxies within the cluster, then increase some probability to see something. So right now you have an observational time, and what is your first object to look at?
Yeah, that's a good point. I mean, so what we decided to do is, of course, you know what others are going. So these guaranteed programs that I talked about, they were public. So you know what others are going to do. And so you try to find a niche, right? You try to find something that no one else is doing, or that they didn't think about, or that they think is too complicated, or that. So what I decided to do is to look at a very special galaxy that a Hawaiian team discovered. They called this galaxy Kola 1, Cosmos Lyman Alpha Emitter 1. It's in a field in the sky called Cosmos. So this is at a redshift of 6.6, and that's at a time where we believe that the epoch of reionization finished, or is in its closing stages. Reionization is this, I think it's important to explain a bit. So after, when the universe formed and after this, the cosmic microwave background was emitted, the entire universe was neutral. And you can basically picture this as there was a big cosmic fog. The fog got heated, the gas got ionized by some ionizing sources, either very hot stars or accretion disks around black holes. So we know roughly when this period happened, this ionization, reionization. But when exactly, how exactly, and where these ionizing photons came from is a bit uncertain. And this is the background of this program, because we know that this galaxy, Kola 1, is quite unique. It's rare, but what's unique is that we know that it resides in so-called ionized bubble. So this reionization likely happened like a cheese, like holes in cheese. We know this galaxy resides in such a hole, an ionized hole. We can measure that based on the spectrum, the Lyman alpha line. We know the size, and we know density of the universe, so we can calculate how many ionizing photons you need to create such a hole. So the goal of this program is actually we know how much you need, and we are going to count whether we can actually see the galaxies that provide those ionizing photons. So we're going to blindly identify these galaxies and count how many ionizing photons they produced. And then we're going to see whether that's enough to power that bubble.
Okay.
If it's not enough, if it's enough, we're happy. If it's not enough, then it likely means that there are like fainter galaxies that are too faint for us to see them, that they have an important role. If we do not need them, then it's likely the brighter galaxies that dominate this ionizing budget.
I have many friends who really like science and astronomy and physics. Can you tell them any words, any suggestions?
Well, doing science is it's a very fortunate position to be able to do it. I mean, we are currently in a pandemic, and there are other challenges that keep a lot of people on Earth very busy. But fortunately, the government still decides to spend some money on very fundamental research without direct impact on our quality of life. Although one could argue with that, because I think there is value in understanding how the universe works. But I think like realizing that I can do that is very motivating and stimulating. It's fun. Science is very challenging. It's very competitive, so it's hard work. I like that. you can work with very advanced technologies. Working with James Webb, which is a $10 billion telescope. I mean, that's just exciting to do.
Yes.
It's also just exciting. What's most exciting is basically every time I take an image with a telescope, and the first time I open it, it's like opening a present box, right? You don't know what's going to be inside. And yeah, I mean, I basically remember the first time I found the so-called CR7 galaxy. I mean, that was a very nice moment because you actually realize, oh, we are actually finding a galaxy at a very high redshift, very high, like the photons traveled 13 billion years before they hit our CCD and we find them. And that's just that idea is very cool. Yeah, so I mean, if people are encouraged by this, I would definitely encourage people to pursue work in science. You can do projects if you study it. There are even citizen science projects like Galaxy Zoo, the famous one. I think that's nice. Yeah, that's basically my what I would say. Yeah, it's I'm happy to be able to do this.
好啦，这就是这一期的内容啦。在之后的视频里呢，我会持续和大家分享 JWST 的动态以及相关的科学研究。那如果你们喜欢物理，喜欢天文，别忘了加关注。我们下期再见吧，拜拜。